Module 8, Section 6.1 Introduction to the Simplex Method. Objectives: be able to formulate maximization problems in standard form. Objective 2, be able to use like variables and set up initial simplex tableau. Objective 3, distinguish the basic and non-basic variables and read solution from a simplex tableau. And Objective 4, find the pivot element of a simplex tableau. Introduction to the simplex method. The geometric method of solving a linear programming problem is limited to problems involving just two decision variables. We use the simplex method for problems with two or more variables. A linear programming problem is said to be a standard maximization problem in standard form if its mathematical model is of the following form. We need to maximize a function p equal to c1 x1 plus c2 x2 plus etc. plus cn xn. This is called the objective function. Then we have a set of constraints which can be written in this form: a1 x1 plus a2 x2 plus etc. plus an xn less than or equal to b, where the right hand side number b has to be a positive number always. It also comes with a set of non-negative constraints which says that all the variables are non-negative. Here is an example of a standard linear programming problem. We need to maximize the function c equal to 5x plus 10y subject to constraints 8x plus 8y less than or equal to 160, 4x plus 12y less than or equal to 180. So these are the two constraints, and the last two constraints will be called the non-negativity condition. Slack variables. To use the simplex method, the constraint inequalities must be converted to equalities. We have these two constraints and we are going to introduce like variables. We need two slack variables here because there are two constraints. The first inequality is converted as an equation using the slack variable s1. 8x plus 8y plus s1 equal to 160. Slack is the same as the deficiency. The second inequality is converted to an equation using the slack variable s2. 4x plus 12y plus s2 equal to 180. Note that the slack variables must be non-negative and we cannot use the same variables as in the original problem. About slack variables. A different slack variable is added to each inequality in the system. The number of slack variables is the same as the number of constraints or inequalities. In the previous example, we have two constraint inequalities, so the number of slack variables needed was 2. The names of the slack variables must differ from variables used in the given constraints. About the simplex method. In a linear programming problem with slack variables, there will always be more variables than equations. Basic variables are selected as the variables corresponding to only one non-zero entry in the column. The remaining variables are called non-basic variables. We obtain a basic solution by assigning the non-basic variables a value of 0 and solving for the basic variables. If a basic solution has no negative values, it is a basic feasible solution. If the optimal value of the objective function in a linear programming problem exists, then that value must occur at one of the basic feasible solutions. Here we are going to consider an example. Consider a standard maximization problem and the associated system of problem constraint equations. Suppose the system of problem constraint equations have 16 variables, including 9 slack variables. Find the number of constraint equations. We know that we need to have as many slack variables as there are constraint inequalities. So the number of constraint equations will be the same as the number of slack variables, which is the same as 9. So there will be 9 constraint equations in this system. Question 2. Find the number of decision variables. We have a total of 16 variables, of which 9 of them are slack variables. So if we subtract 9 from 16, we will get 7 remaining variables which are called the decision variables. And question 3, find the number of basic variables and non-basic variables. There are as many basic variables as there are equations in the system. The remaining variables are called non-basic variables. Since the system has 9 problem constraints, there are 9 basic variables. The remaining 7 are non-basic variables. Find the number of linear equations formed by setting the non-basic variables equal to 0. Setting the non-basic variables equal to 0 does not affect the number of constraint equations in the system. The system has therefore 9 linear equations. Here is an example. Consider the maximization problem. Maximize c equal to 6x1 plus 3x2 plus x3, which is the objective function, subject to 2 constraints, and we have the last 3 inequalities representing the non-negativity condition of the variables. How many slack variables are needed? We only have 2 genuine inequalities here that are the constraints, so we need 2 slack variables to convert them into equations. So the answer will be 2. 2 constraints and 2 slack variables. Now if we call the slack variables to be s1 and s2, the first constraint can be written as 7x1 plus 5x2 plus 8x3 plus s1 equal to 161. Notice that this is an inequality and here it is an equation. So this will be the first equation in the system. And the second constraint can be written as an equation using s2 added to the left side. So this will be s2, slack variable s2. We are going to look into the simplex method, how to start the process. We have a problem here to maximize p equal to 5x1 plus 10x2 subject to 8x1 plus 8x2 less than or equal to 160, 4x1 plus 12x2 less than or equal to 180. 2 constraints. We might want to notice that the simplex method can be used to solve larger systems that contain several variables. First, what we need to do is we need to introduce slack variables and rewrite the problem as a system of equations. So the first constraint is converted to an equation using the slack variable s1. Second constraint is converted to an equation using the slack variable s2. And the third equation in the system is the same as the objective function written with the right hand side equal to 0. So remember, our objective function was maximize p equal to 5x1 plus 10x2. We always write the equation so that the coefficient of p, the objective function, is 1. So we need to move this 5x1 over to the left side, 10x2 over to the left side, getting this last equation in the system. Now what we are going to do is we are going to set up what is called the initial simplex tableau. The initial simplex tableau is essentially the same as an augmented matrix coming from the system of equations we created. So we have the decision variables x1, x2, and the slack variables s1, s2, and the objective function variable p, which is also a decision variable. So we write the coefficients in the system of equations. Our first equation was 8x1 plus 8x2 plus s1 equal to 160. So the coefficient of s2 will be 0, coefficient of p will be 0 for the first row. So likewise we create the second row as the coefficients of the second equation, the third row as the coefficients of the third equation. We usually separate this by vertical line and horizontal line. The last row is special, which is called the decision row. So we separate that using a horizontal line. The right hand side of the equations will be separated by a vertical line like this. At any stage of the simplex method, we can read a solution from the tableau. So this is how we do that. So we separate the variables into what is called basic variables and non-basic variable. A basic variable always has just one non-zero entry in that column and the rest of the entries are 0. So if you look at this tableau here, the variable s1 has got a column with only one non-zero entry. So s1 is a basic variable. So this will be a basic variable. And so is s2. It has got only one non-zero entry here. So s2 is also basic. And the variable p is also basic. These are the 3 columns with only one non-zero entry. So once we separate the basic variables, The remaining variables in the system are called non-basic. So we have three variables which are, actually we have two variables which are non-basic. x1 and x2 are non-basic variables. In order to read the solution at this stage, what we do is we put the non-basic variables to 0. So that means in this case we need to put x1 equal to 0 and x2 equal to 0, which are the non-basic variables, and then we need to solve for the remaining variables using the equations. So if we read the first equation from the first row, 8x1 plus 8x2 plus s1 equal to 160. Notice that x1, x2 are already zeros. That gives you the value for s1. 1 times s1 equal to 160. So we get the value for one of the three basic variables. If we use the second row, again with the same conditions, x1 and x2 being zeros, we will get 4x1 plus 12x2 plus 0s1 plus 1 times s2 plus 0 times p equal to 180. So that equation will be simplified as s2 equal to 180. So we get the second basic variable, and from the last row we will get p equal to 0. Determining the pivot element. In a simplex tableau, in order to process the tableau further, we need to determine the pivot element. This is how we do that. The most negative element in the last row, which we call the decision row, will be corresponding to the pivot column. So in this case, negative 10 is the most negative number. So the second column is going to be the pivot column. So this is the pivot column. And in the pivot column, we will consider the positive numbers, only the positive numbers in the pivot column, and divide the numbers in the last column by the positive numbers in the pivot column, like 160 over 8. So that ratio will be 20. Then we have 180 divided by 12, which will be giving 15. So in order to decide the pivot row, we take the least ratio. So in this case, the least ratio will be 15. So that corresponds to the second row. So our pivot row will be the second row, which is labeled as S2. So we have the pivot column and the pivot row, and they intersect at 12, and that will be the pivot element. So we have the pivot column corresponding to the least negative number in the last row, and the pivot row corresponds to the least ratio when you divide the last column entries by the positive numbers in the pivot column, and the common intersection will give the pivot element. We also call x2 as the entering variable and s2 as the exiting variable. Notice that x2 is a non-basic variable now, and s2 is a basic variable now. But if you actually process this tableau, the roles will be interchanged in the next stage. That's why we call entering variable and exiting variable. Let's do an example. Introduce like variables and then write the initial simplex tableau for the given linear programming problem. Notice that this is a standard maximization problem. We have the objective function c equal to x1 plus 5x2, and we do have three constraints here. So we need three like variables, s1, s2 and s3. So the equations in the system will be x1 plus 2x2 plus slack variable s1 equal to 14. So that is taking care of the first constraint. Second equation will be 6x1 plus x2 plus slack variable s2 equal to 10. Takes care of the second constraint. Third equation will be 9x1 plus 2x2 plus third slack variable s3 equal to 10. So that is the third constraint. Notice that these are the non-negativity condition. We don't need to worry about it now. And then the last equation in the system will be the objective function rewritten with the coefficient of c being 1. So I need to rewrite this as negative x1, negative 5x2 plus z equal to 0. So that is another version of this objective function here. So we do have 4 equations. Now to write the initial simplex tableau, we need to convert this into an augmented matrix form. So we are going to label the columns here, x1, x2, then you have s1, s2, s3, then we have p, then we have the space for the right hand side. So and then I need to write the coefficients in that order. 1, so we are taking the first equation, 1, 2, s1 coefficient is 1, s2 is absent, so it will be 0, s3 is again absent 0, p is absent 0, right hand side will be 14, that will be the first row. So likewise you fill up the remaining entries, 6, 1, 0, 1, 0, 0, 10, then we do have 9, 2, 0, 0, s3 is 1, then p is 0, right hand side is 10, and now we are writing the last row, so I am going to separate it by a horizontal line. Coefficients will be negative 1, negative 5, s1, s2, s3 are absent, so the coefficients will be 0, 0, 0. The objective function variable is z with a coefficient 1, so that will be here, right hand side is 0. And these rows are labeled as s1, s2, s3, corresponding to the slack variables and the constraints. So this is what we call the initial simplex tableau corresponding to this standard maximization problem. In the next example, we are given a simplex tableau and we need to read the solution from here. So what we need to do first is we need to identify the basic and non-basic variables. The x2 column contains only one non-zero entry here, so that means x2 is basic. The x3 column contains only one non-zero entry here, so x3 is also basic. And I can say that s2 is basic because of there only one non-zero. And the C also has got only one non-zero basic. So these variables are the basic variables. So we do have x2, x3, s2 and c as the basic variables from this simplex tableau. The remaining variables will be non-basic. So we have x1 non-basic, s1 non-basic, s3 non-basic. What we need to do is, in order to get a solution, we need to set all those variables to be zeros, non-basic variables to be zeros. So x2 will be 0, s1 will be 0, and s3 will be 0. Those are the non-basic variables. Now we are going to read the equations using the rows. If you read the first row, it will be like 3 times x1, 0 times x2, 11 times x3, negative 7 times s1, 0 times s2, plus 0 times s3, plus 0 times c equal to 17. So that means some of these variables will have 0 values. The only non-zero entry coming out of that will be 11 times x3. Everything else will be zeros because of the multiplication. So we get the equation 11 times x3 equal to 77. So which will help me to solve for x3 equal to 7. So this is the first solution, one of the basic variables. Now we can read the second row exactly the same way. You multiply the coefficients and the variables and use the assigned values x2, 0 and so on. So we get the equation 3 times x2 plus everything else is 0 if you multiply, coming back to negative 15. So 3 times x2 equal to negative 15 will give x2 equal to negative 5. So basically repeat. Third row converted to an equation will be 2s2 will be equal to 8. Everything else is 0 because of the multiplications. So s2 will be 4, third value. And the last equation will be negative 5 times 0, 0 times x2, so that is 0. So if you keep on adding like that, left side will be 2 times z, on the right side will be negative 28. So 2 times C equal to negative 28 will be giving C value equal to negative 14. So our solution will be 3 non-basic variables taking value zeros and the remaining 4 basic variables getting these values through the calculations. So this will be the solution from this tableau. Here is another example where we need to find the pivot element of the simplex tableau. We require the pivot element in order to process this tableau further to take us to an optimal solution. Remember that. So the pivot column is the column containing the least negative number in the decision row or the last row. So if I scan the last row, we do have 2 negative numbers and the least one is negative 3. So this will be the pivot column. So we have the pivot column here. So pivot column is the first column. So now we need to decide the pivot row. In order to decide the pivot row, I need to look in the pivot column and consider only the positive numbers. So when I take the positive numbers and divide the numbers in the last column by the positive numbers in the pivot column, we will get these ratios. 11 divided by 4. That will be between these two corresponding entries. 11 divided by 4. Then the next one will be 19 divided by 3. And we also have the next one, which is 25 divided by 1. These are the 3 ratios. We have 3 non-negative entries here or 3 positive entries in the pivot column, and the ratios are like this. We always go with the least ratio. So of these 3 numbers, 11 by 4 is the least one, because this will be 2.75 and this is nearly 6.3 and this is 25. So we go with the least ratio, which is 2.75, and the row corresponding to that will be the pivot row. So if I mark the pivot row, it will be the first row here. So the pivot row is the first row, and the pivot element is the element which falls in the pivot row and the pivot column, which will be 4.